Okay, so today I begin with the compass part of theorem 1.3.11. All right, so it states that the rows of a matrix form a linearly dependent set if and only if there is a zero row in any row echelon form of that matrix. Okay. The overpath okay, so it has been done last Wednesday. All right, so now I will continue with the reverse part. So the reverse part says that if there is a zero row in any row echelon form of a matrix, then the row of that matrix form a linearly dependent set. Okay. Right. Okay. So we let U right. So U be a row echelon form. All right, of A with a zero row. All right, so if we have a row echelon form with zero row, then the last row of the row echelon form should be a zero row. Okay, so the last row of U must be a zero. All right, so this row echelon form may have more than one zero row. It's possible. But once it has a zero row, then the last one should be a zero row. Because recall the definition of a matrix in row echelon form, you will see that we have to move all the zero rows into the bottom of the matrix. Right? So all the zero rows should move to the bottom of the matrix. So if there is a row or zero row in the row echelon form, then the last one should be the zero row. Okay. All right, so since there is an invertible matrix G such that R1 prime, and the last row is your row, which is U. U is in row echelon form. And we know, and the G, what is G? As you know, G actually is a product of elementary matrices, right? Each elementary matrix corresponding to one elementary row operations. So we can render a matrix in row echelon form by applying a sequence of elementary row operations on A. Okay, so G is just the product of the corresponding elementary matrices. Okay, and G, of course, should be invertible, as we mentioned several times before. So, okay, so let me write down the entries of the G matrix, G11 and G12, G1M. I found a typo in my lecture notes. I typed GMM. Actually, it's incorrect. It should be G1M. I'm sorry. So please correct it. And GM1, GM2, and GMM. Okay. And R1. Okay. So A has M rows here. Now, so the last row of U is 0, right? And the last row actually is the last row of the G matrix, right? Multiplied with the column vector of the row vectors. Okay. So that this gives us that 0 xg m1 r1 plus gm2 r2 plus gmn mm rm. Okay, 0 is that one. All right, so we have a linear relation, which is a linear relation on the rows of A. Okay, so it's a linear relation. Now, since G is invertible, okay, since G is invertible, it has no 0 rows by lemma. So we proved the lemma 1.3.b last Wednesday. So when G is invertible, then no row becomes 0 rows. So every row should be non-zero. Okay, every row should be non-zero. So that especially the last row is a non-zero row. So at least the one of the entries to be non-zero. Okay? So that's the M component GM1, GM2, GMM of the last row of G are not all zeros. And then G M1 R1 plus G M2 R2 plus plus G MM RM equal to 0 it's a non-trivial linear relation on the rows of A. All right, so we have a non-trivial linear relation on the rows of A, and which shows that the index set of row vectors of A is a linearly dependent set. Okay, so this is the end of proof. Questions? Now we discuss next theorem about column vectors of a matrix. The column vectors of a matrix, okay, form a linearly dependent set. Okay, if and only if there is a column, there's a column having no pivot position. Okay, right. So you can compare the two theorems here. The theorem gives us a necessary and sufficient condition for the rows of a matrix form a linearly dependent set, right? It gives us a justification. And this theorem gives us a necessary and sufficient condition that the column vectors of a matrix form a linearly dependent set. Okay, so okay, for column vectors, the necessary and sufficient condition is that there is a column of the matrix having no pivot positions. No pivot position. All right, so we recall of a theorem we proved previously, 1.3.c, that the column vectors of a matrix A form a linearly dependent set, right? If and only if the homogeneous linear system AX equal to 0 has non-trivial solution. Okay, has a non-trivial solution. Okay, means that the kernel of A is not equal to the set of zero vectors. Okay. But this condition, if and only if there is so there is at least one free variables. Okay, in describing the solution set. The solution set is just the kernel of A. Okay, of AX equal to 0. All right? So now, by theorem 1.3.8, right, this is equivalent to that there is a column of A having no pivot position. Because if there is a column has no pivot position, then in the reduced echelon form, that column has no pivot. If a column has no pivot, then the corresponding unknown variable can be set to be free. Okay, can be set to be free in theorem 1.3.8, right? We proved that before. So in terms of pivot positions, that such a column has no pivot position. Okay. Any questions? Okay, another way to state theorem 1.3.12 is the next theorem. The column vectors of a matrix form a linearly independent set. So this time, to form a linearly independent set, if and only if there is a pivot position in each column of that matrix. So actually this is equivalent to theorem 1.3.2. Know that P if and only if Q is equivalent to not P if and only if not Q. Logically, right? Remember the appendix A, that if P and Q are if and only if conditions, then their negative are if and only if conditions. Any questions? Okay, so we just finished chapter 1. Okay. So chapter one will be the very basic materials were used in this semester. So from time to time, we will refer back to chapter 1. Okay. And so I ask you to read chapter 1 carefully, especially many theorems and concepts. You should. It's better for you to put into your heart. That means that into your memory. So whenever you want to use it, it will occur to you, and then it will help you a lot. All right, because as you see, any branches of mathematics, it's just like piles. You know that the things always on top of something in the basics. So the construction of the mathematics is from the ground to the high skies. Without the ground, there's no high sky, right? So, okay, so let's move to chapter 2 on vector space. Okay, so we will go from a very concrete one to a very abstract one. All right. The concrete one is we encountered Euclidean vector spaces. Okay. Rn consists of the set of all n-dimensional column vectors, and the components of the column vectors are real numbers. Right, so Rn is this set, and is the set of all n-dimensional real column vectors. All right, and it's called the n-dimensional real Euclidean vector space. So it's a concrete vector space we are all familiar with. Of course, if the components are complex numbers, then we will have C. So similarly, in later parts of this semester, okay, the Cn is called n-dimensional complex Euclidean vector space. Okay, so this one is also very concrete. Okay. Remark. As you see, to write a column vector, it will take, because it's vertical, right? So it will take, well, sometimes we get a lot of space. So for the convenience, Okay, for the convenience of writing a column vector all right, so column vector like this one can be written as an n-tuple enclosed by parentheses, okay, by using the parentheses. Okay. By using parentheses. If we write vector in this way with brackets, we mean a row vector. All right, so it's just a convention for us to write column vectors using n-tuple, so enclosed by parentheses. If we enclose by brackets, then it's interpreted as row vectors, so it's a row vector. Okay. Okay, so we know a lot about Euclidean vector spaces. Okay, so I ask you to read the textbook on this section. So I want to devote my energy to the second section about line, planes, and the hyperplanes. Okay, and I will end up with a very general setting, okay, about affine space in n-dimensional Euclidean vector space. Okay, before that, I would like to enumerate several spatial examples. All right, first one is about lines, okay, in R2. Right, in the plane, you're all familiar with lines since the junior high school. Okay, suppose we are in R2. All right, so this breadboard is just similar like a plane, right? So in R2, so if R2, so maybe we write down this way, and so we have 2 points, U1, U2, another point, V1, right? Suppose we have 2 points in the plane, and by Euclidean geometry, these 2 points determine one and only one line, right? So we can, so it determines one and only one line. We call L here. And in junior high school, you learn how to describe this line. There are quite a few different ways to describe such a line, okay? And because we are now in linear algebra course, so we try our best to describe a line in terms of language of linear algebra. Okay. And you will see this language gives you ability to extend the idea into high-dimensional Euclidean space, okay? And not only for lines, okay, but for some very beautiful geometric objects. All right, so a way to describe it is that we pick up a point. So our job is to describe points on the line, right? So suppose we have an arbitrary point. Okay, so this is an arbitrary on L, right? It's an arbitrary point. And as Euclid told us that this L line is determined by these 2 points. So any point on the line, the component should be able to write down by using the information about these 2 points, i.e. their components, U1, U2, V1, V2. Okay? So let's see how to do it. Well, so one way we learned from maybe junior high school or high school is that we use vector, right? So, okay, we construct vector here, right? Okay, and so now remember this is corresponding to a column vector because we use parentheses, so it's a column vector. And this vector, so this is actually a point as well, and represented by a vector, right? So this is the origin here. Okay, we select this point as the origin of the plane. All right, so we have this one, the x. And also we have another vector u here. All right, so again, remember this is actually, right? This is another way to write down a column vector, just like here. All right, and the v vector. Okay. Now we select you can see if now we select u as the base point, we construct a difference vector. All right, so this difference vector is v minus u. Okay. And also now the difference vector from u to x is x minus u. Okay. Now because that they are these 3 points are on the same line, so you can see that this difference vector and that difference vector, the red one and the green one, they are parallel to each other. Okay, and so that the L, a description about that is that the difference vector is proportional to this difference vector. Okay, and as we learned from high school, that if we round the t to all possible real numbers, then the point x will run over all the points on the line L. Okay, so a description of a generic point or an arbitrary point on the line L, okay, should satisfy this equation with the parameter t. Okay, and so that okay, so the line So the line determined by 2 points. Is a set of points described by by all the points in the plane, such that the difference between x and u, the green vector, is to the proportional to the red vector. All right, or sometimes you may describe it by saying that x is equal to u plus t, v minus u. Okay, and which is called a parametric representation of L, the line L. Okay? Right, so we end up with a parametric representation. All right, this is one of possible descriptions of a line determined by two distinct points. This is one way to describe it. Now we would like to describe a way, all right, related to linear algebra. Okay, so now x is a point on the line L determined by u and the v. Okay? If and only if the x can be described by okay, for some parameter t in R, right? So that's if and only you can. This is from the parametric representation. Okay, and now we move u to the left-hand side. So we have x minus u1, y minus u2. This is x minus u, which is equal to t, v minus u, is t, v1 minus v2. Sorry, u1, v2 minus u2, okay, for t in R, for some t in R. If only if v1 minus u1, v2 minus u2, t equal to x minus u1 minus u2, right? For some t in R. Maybe I will write it more specific. Okay, so that says that this linear system is a metric equation. This linear system has a solution. Okay. So if and only if the linear system v1 minus u1, v2 minus u2 is consistent. Okay? So this is our description. Consistent. So a point x, right? X is the point on the line L determined by u and v if and only if a linear system is consistent. So this is our language, right? Linear algebra. Questions? So we take an example. Okay, L is determined by u equal to 1, 3, and v equal to 2, 1. All right, so x is on L if and only if 2 minus 1 and 2 minus 1 and 1 minus 3 t equal to x minus 1, y minus 3 is consistent. Okay, now using the augmented matrix, so we have this is 1, this is minus 2, x minus 1, y minus 3, similar to, so by using row operation, we eliminate this entry by multiply with 2, by the first row multiply with 2 and add to the second row. So we have okay, so this one is consistent, right? It's consistent. Now, this augmented matrix is consistent if and only if what? This entry is 0. So if only y minus 3 plus 2 x minus 1 is 0. All right, so we end up with an algebraic equation, right, to describe the line L. Okay, so from the parametric representation, we end up with an equation. Thus, the linear equation 2x plus y equal to 5 represent the line L. Okay? Of course, in high school, you learned how to find a linear equation, right? To describe a line. Of course, you know how to do it, right? There are quite several ways. But here, I developed the result by using the concept in linear algebra. And this approach, as I just mentioned before, well, will give us a wide open road to look into more general situation, not just only line only. Okay, so any questions? So we just related to the concept of consistent linear system. Okay. Okay, I think I stop here, then so we can have a break for 10 minutes. Okay. Okay, so we go on. All right, so I'll study lines in n-dimensional Euclidean space. Okay, so now we are in n-dimensional Euclidean space. So, suppose we have a point. We have select a point called the origin of the Euclidean space. And again, we have 2 points, distinct points, U and V. All right, so we have 2 distinct points. And these 2 points, again, determine a line in Rn. So it determines this error here. Okay, and similar ideas. Okay, we construct. So suppose we have so X is a point on the line L. And again, so we have V minus U, and the difference vector X minus U here. Okay, so now again, so a parametric representation of the line L, it's such that X is equal to U plus T V minus U for T in R. Okay, and so we let an example. Consider an example here. So we consider a line L in R3 determined by U, which is 1, 0, minus 1, and V, which is 2, 1, 2. Okay. So now, in 3-dimensional Euclidean vector space, a line, again, by Euclidean geometry, these 2 points, they are distinct, you can see, and determine a line. So that X, Y, Z is on L. So if and only if we have is equal to U plus T, and this is U1, U2, so that it's 1, 0, minus 1 plus T, and difference 1, 1, and 3. for some t in R. Okay, so this vector is the difference between V and the of V from U. So 1, 3 here. Okay, so now we can write down x minus 1. So we move this column vector to the left-hand side. X minus 1 is y, z plus 1. Okay, so we consider this one. So this is linear system should be consistent. Okay, it should be consistent. Okay. Okay, so we go on by using augmented matrix. Is consistent. Right, and then by row operations. Okay, we have should be consistent. Okay, so the if and only condition is that these two entries must be 0. So we have y minus x minus 1 equal to 0, and z plus 1 minus 3x minus 1 is 0. Okay, so finally is y minus 1 is 1, and 3x minus z is equal to 4. So we need to algebraic equation to represent a line, okay, in the three-dimensional Euclidean vector space. At this moment, then you can imagine, or you can extend to say that to describe a line in n-dimensional Euclidean space, you need n minus 1 linear equations. Okay, so but we will prove that later. Okay, in a general setting. You all know this in high school, I believe. Okay. The difference is that I just use the concept we studied in linear algebra to derive the system of linear equations only. All right, so we consider planes in three-dimensional Euclidean space. Okay, so by Euclidean geometry, right, 3 non-collinear points. All right, so the keyword is non-collinear. Three non-collinear points, U, V W in R3 determine a unique plane in R3. All right, so this is we learned from Euclidean geometry. 3 non-collinear points. All right, so we think about we are in the 3-dimensional space, and we have 3 points. Okay, so this is U, this is V, this is W. And we say that 3 points, actually this is the 3-dimensional space here, and we have 3 points, okay? And we say that they are non-collinear, right? So it's a concept, a word, but how do we describe it mathematically, especially in terms of language in linear algebra? So, so that just 3 points, all right? So let's see the converse of this statement. So 3 points, U, V, W in R3 are collinear. Collinear. Collinear means that they are on the same line, right? This is the way we say collinear, right? On the same line. So that we have a line, and U here, V here, and the W here. All right. So if we can find a line, now this line goes through these 3 points, then we say these 3 points are collinear. Okay, and so you can see that from the geometry, you see that it's collinear if and only if the difference vector are proportional to each other. Okay, so here. So they're proportional to each other. Or okay, for some T in R. For some T in R. And so this means that in linear algebra language, one times T times equals 0 over so you can see at least one of the coefficients is non-zero. So that means that the set of two vector, this set is a linearly dependent set. So collinearity of 3 points, can be described in terms of a concept called linear dependency, right? So that you can select V as base. So U minus V and W minus V, these two vectors form a linearly dependent set. Once we know a description in terms of linear algebra to collinearity, then what is non-collinearity? Non-collinearity is the opposite of linearity, and the opposite of linear dependency is linear independence, right? Okay, so oh, okay, yep. Okay, so that's 3 distinct points U, V, W are non-collinear in R3 if and only if U minus V, W minus V, these two vectors form a linearly independent set. Okay, a linear independent set. Okay, so the Euclidean geometry here tells us if 3 non-collinear points determine a unique plane, right? So we have to describe it. So this plane, so the plane, all right, H determined by U, V, W, it's okay, and so, all right, so let's see. So now it determines a plane, of course. So, we have okay, all right, and this is U minus V, and this is W minus V, okay? And because these 3 points are non-collinear, so these two vectors form a linearly independent set. And it determines a plane, and if we have a point X on the plane, then as we know, how do we get into there? Well, we can use the vector. So we can form so that by the parallelogram diagram, so this is parallel to that, parallel and the parallel Okay, so so we have, all right. So this part is this is S times U minus V. Okay, so it's a multiple of this vector. Okay, this is yellow. Yeah, it's yellow. Orange. Okay. Pretty much like orange. Okay. Anyway, so this vector is a scalar multiplied with the orange vector. And also we have this one. This is t times minus u. Okay, so this is also a multiple of the green vector. And these two vectors add together to get you the x minus v. Okay. So that so x is the point. All right. So the plane consists of all points such as x minus u minus v. Okay, is equal to x u minus v plus t dot minus v for t s in R. Okay. I forgot to put TS in R in my lecture notes, so please edit. All right, so so when we vary S and T over all the real numbers, then we can find out all the points on the plane. Okay. Okay, and which is a parametric representation of the plane in R3. Okay, so now with three non-collinear points, then we can write down a parametric representation of the plane H. And we know that these two vectors form a linearly independent set. Okay. Okay, now a point x in R3 is in the plane H if and only if that x minus v is equal to x u minus v plus t minus v. Okay? For some xt in R. And so this is if only if the linear system so if only the linear system that u minus v minus v st equal to x minus v. So the linear system is consistent. Okay, and that means that u minus v, minus v, and the x minus v, the augmented matrix is consistent. Okay, it's consistent. Now take an example. Okay. Consider u 1 0 minus 1 V is 220, and the W is 011 in R3. Okay? Now, since U mass V, which is U mass V, which is mass 1, mass 2, and the mass 1. One more adder here. Because, okay, so this is minus 1. Wow. And the W minus V, which is minus 2, minus 1, and 1. Okay, these two vectors, you can see, form a linearly independent set. Okay, it's easy to check, right? We already have the tool to check them. So that linear independent set. So U, V, W are non-collinear. Okay, so that they determine a plane H. Okay. Okay, and so X is in the plane if and only if. So now we use this one. This is augmented matrix. So U mass V is minus 1, minus 2, and minus 1. This is the first column. And the second column is minus 2, minus 1, and 1. Okay, and the X minus 2, Y minus 2, and the Z. Okay. All right, it's consistent. So, wow, maybe. Okay, so maybe I go to here. Maybe I just change. Probably I change this one. It's simpler. Okay. So it's 1. So without change too much. I'm sorry, so I decided to change the component of U. It's simpler. Sorry. Okay, I changed my mind, so I changed this one. Okay, so so that by row operations, I will end up with okay, so this one is consistent. All right, so we have pivot positions there. So they are pivot positions. And so this is become too consistent if and only if the last entry should be 0. Should be 0. And so this is if and only if x plus y plus 3z equal to 4. Okay. So once again, as we well know that a plane in the three-dimensional Euclidean space can be described by a single linear equation, just one. Okay, so that is the case. Okay, and so now I will now give a general picture about the object in Euclidean geometry. All right, so we will study affine space in Rn. All right, so we let U1, U2 up to UK and UK plus 1 be K plus 1 points in Rn. So suppose we have K plus 1 points in Rn such that the set U1 minus UK plus 1, U2 minus UK plus 1, UK minus UK plus 1. All right, so it's a set of K vectors. These K vectors is a linearly independent set. All right, so we require that we have K plus 1 points and select U K plus 1 as a base. So we form K difference vectors there. All right, and we ask for that this set is a linearly independent set. Then the set of points in N, right, defined by x equal to the base point UK plus 1 plus T1 U1 minus UK plus 1 plus T2 U2 minus UK plus 2 plus TK UK minus UK plus 1 and T1 T2 TK is in R. Okay, so it's a set of points, and the points is obtained by a linear combination of these vectors in a linearly independent set plus a base point UK plus 1. And such a set is called the K-dimensional. Okay, the K-dimensional affine space in Rn determined by U1, U2 up to UK plus 1. Okay. So the linear independency of this set characterizes the dimension. Okay, the dimension of this affine space. and give us the degree of freedoms to put the coefficient here. Okay. And T1, T2, T3 up to Tk can be arbitrary, so that's why we have k degrees of freedom. And so that is in here given the name k dimensional for that. All right, so this is called the affine space. All right, so that's a line in Rn is one-dimensional. It's a one-dimensional affine space in Rn, and a plane in Rn is two-dimensional affine space in Rn. Now, a particular one is an n-1 dimension. An n-1 dimensional affine space H in Rn will be called a hyperplane in Rn. Okay, so so a hyperplane in n-dimensional Euclidean vector space is just n-1 dimension, just one dimension less than Rn. Okay, so it's n-1 dimensional affine space in Rn. Okay, so now, you know, such a representation of an affine space is a parametric representation. And so, as we did before, we ask how many algebraic equations do we need to describe a k-dimensional affine space? All right, so this gives a theorem 2.2.8. Now, a k-dimensional, okay, a k-dimensional affine space H in Rn can be represented by a system of n minus k linear equation with n unknowns. Okay, so a k-dimensional affine space can be represented by a system of n minus k. The number of linear equations n minus k with n unknowns. All right, so we give a proof. All right, so let H be the k-dimensional affine space determined by k plus 1 points u1 up to uk plus 1. in Rn with, as we know, with the set u1 minus uk plus 1 uk minus uk plus 1, a linearly independent set. Okay. All right. So that x so a point in the n-dimensional Euclidean space is in the hyperplane H, in the affine space H, if and only if, okay, so if and only if there exists a T1, T2 up to Tk such that x is equal to u k plus 1 plus T1 u1 minus u k plus 1 plus plus Tk uk minus u k plus 1. Okay. Right. And so in terms of a linear system, we have okay, so each one is a column vector. Okay, each one is a column vector, and the dimension of the column vector is n. Then it's equal to, okay, so let's check the dimension of this matrix equation. This is a matrix, dimension is n times k, okay, and the unknown vector is k plus times 1, and this one is n times 1, okay. So we ask for that this linear system is consistent. Okay, and we call this coefficient matrix A matrix. Okay, and this is T matrix, and this is the right-hand side matrix is B here. Okay, so now by using the augmented matrix u1 minus uk plus 1, the first column u2 minus uk plus 1, the second column uk minus uk plus 1, the case column, and x minus uk plus 1. Okay, so this is basically is A, B. Okay, so the augmented matrix is consistent. Okay, any questions up to now? So that x is a point in the affine space H, if and only if this augmented matrix is consistent. Okay. All right, and so we expand the augmented matrix. All right, sorry. Okay, so here is U11 minus UK plus 1, 1. U21 minus UK plus 1, 1. UK1, UK plus 1, 1. And X1 minus UK plus 1, 1. All right, U12, UK plus 1, 2, U22 minus UK plus 1, 2, UK2 minus UK plus 1, 2, X2 minus UK plus 1, 2. And the last row is U1n minus UK plus 1n, U2n minus UK plus 1n, UKn minus UK plus 1n, and the xm minus UK plus 1n. Okay, so again, this is A and B. All right, so we also ask is consistent. Okay, and we let U, C be the reduced zero echelon form of the augmented matrix A, B. All right, and it is clear that each component, okay, of the last column C, C1, C2 up to Cn of the augmented matrix, it's a linear combination of the component of the last column B U A, B. So, because when we do the row operation on the augmented matrix to render this row reduced row echelon form, then when we do the row operations, we actually multiply over either exchange or we multiply some constant scalars and add to another rows, right? So when we do so all this is elementary row operations, then every component in the last column C here, C1, C2, Cn, must be a linear combination of the components of the last column of B. So we have Ci can be written as alpha 1 x1 minus u k plus 1 plus alpha I2 x2 minus u k plus 1 2 plus alpha in xn minus u k plus 1n. Okay. So for each I, okay, so Ci is just the linear combination of the components of the B in B vector. Okay. For some scalars, alpha ij, I equal to n. Okay. So I from 1 to n, and the j is from 1 to n there. Now, sinks, all right? Now, as we know, these vectors form columns of A. Okay, these vectors form columns of A. So, since the columns of A form a linearly independent set. Okay? Each column of A has a pivot position. Okay? By theorem 1.3.13. This is the last theorem in chapter 1 we studied. Okay, so that every column of A has a pivot position. Okay, and then U has K pivots because we have K columns. Every column has a pivot position, so that in this reduced row echelon form, we have K pivots in the first K rows. Okay, so in the first, because we have n rows, and remember the dimension of U. U is n times k, and this C is n times 1. So U has k columns but n rows. And we know that the U has k pivots. Every column has a pivot because the columns form a linearly independent set. Okay, so they are so that these pivots should be in the first k rows. Should be in the first k rows, right? And the rest, n minus k rows. So, right? Now, so since the augmented matrix U C is consistent with all right, since the augmented matrix, let me write it down. R1 prime, RK prime, 0, 0, C1 up to CK, CK plus 1 up to Cn. Okay, so we know the k pivots should be in the first k rows. So the rest of the rows should be all 0 rows. Okay, so here we have all 0 rows here. Now, the augmented matrix is consistent. Okay, so that means that the CK plus 1 up to Cn must all be zeros. So we must have, okay? So we must have Ci equal to alpha I1 x1 minus uk plus 1, 1 plus alpha I2 x2 minus uk plus 1, 2 plus plus alpha In xn minus uk plus 1n should be equal to 0 for all I from k plus 1n to n. Okay. All right. So this is a linear equation. Okay. Okay, so we conclude that x in Rn is in the hyperplane if and only if alpha I1 x1 plus alpha I2 x2 plus plus alpha In xn is equal to alpha I1 uk plus 1, 1 plus alpha I2 uk plus 1, 2 plus plus alpha In uk plus 2n, right? For all I from k plus 1 up to n, right? Okay, so which is a system of n minus k linear equations in n unknowns. Okay, and this is the end of the proof. Okay. All right. Okay, so we prove our theorem that a k-dimensional affine space in Rn can be represented by a system of n minus k linear equations with n unknowns. Okay. Okay. Any questions? All right. So if no questions, then I stop here. All right. And I'll see you next Wednesday. And hey, yeah.